start classes a bit late, like maybe 10 minutes late, but since the room is already pretty full, I think I'll actually get started now. You might notice there's quite a few people in the room. The class is quite a bit oversubscribed, so if you're not an enrolled student, we'd ask that you do give up your seat to students who are enrolled in the class, because there's actually more of them that can fit in this room. We are broadcasting the lectures live on YouTube, and they're also being recorded, so there will be a link on the course website. In fact, the link should already be there, and you can go there if you can't make it to lecture, or if there's not enough space in the room. All right, so let's get started. Hopefully all of you are here for Deep Reinforcement Learning, CS294-112. We'll start with a little bit of course logistics, and then we'll talk about some motivation for why we want to study deep reinforcement learning, and a few words about what we'll cover in the class. All right, so my name is Sergey Levin. I'm the instructor for this class, and then we have two GSIs this semester, Abhishek Gupta. Abhishek, can you stand up? And then Josh Akiam, and Josh is actually not here today, but both Josh and Abhishek will hold office hours, and that'll be posted on the course website. So that's the course website. That's the most important link on the slide, so please do check that out. There's a Piazza system set up for the course, so everybody who is enrolled should go and sign up for that. That's what we'll use to contact all of the students. And if you are not an enrolled student in the class, but you'd like to follow along, we have actually a subreddit set up. So for students who are not enrolled, we ask that if you have questions or something like that, you can go ahead and post them on the subreddit. Other students might be able to answer, or other people following along the class, and the TAs will occasionally check in on that as well. If you're an enrolled student, please go ahead and sign up for Piazza. So we won't have office hours today, but starting next week, we'll have office hours on Mondays and Wednesdays, Abhishek, at 1 p.m., right?
1 to 2 p.m.
Yeah, 1 to 2 p.m. The GSIs will hold office hours. I'll also set up a slot for my office hours, which I'll post on the course website sometime over the weekend. So starting next week, we'll have regular office hours. For the office hours, we would ask that if you want to come to the office hours, we'll actually have a link to a spreadsheet on Piazza, and you go in there and you put in your name just so that we know how many people will sign up. And that way, if you see, like, at 1 p.m. there's like 3 people that want to come, maybe come a little later at like 1:20 p.m. So that's mainly to distribute the load and let us know roughly how many people to expect. Okay, so prerequisites and enrollment. This is an advanced graduate level class, so we expect everybody who's enrolled in the class and taking the class for credit to have taken a machine learning course before. If you took classes at UC Berkeley, we'd expect something like CS189, 289, or 281A. If you are a graduate student and you took an equivalent class in your undergraduate or master's institution, that also counts. Online class, like a Coursera class, doesn't meet the prerequisite, but if you took like an advanced undergraduate or graduate level machine learning class, that counts. And if you're not sure, then please email me and let me know which class you think meets that requirement for you. We expect by default everybody to enroll in 3 units. You can enroll for less units. That won't change the content of the class or the grading standard in any way. If you want to enroll for 4 units, please let me know. There is a pretty long wait list. We will be inviting students off of the wait list, probably starting today, roughly in order of priority, with computer science PhD students receiving the first priority. So we will start processing that today. If you're on the wait list, please be patient. Yes?
Is it the website waitlist, not the Cal Central?
Correct, yes. So we're not using the Cal Central waitlist. If you want to get on the waitlist, or you're on the Cal Central waitlist, please go to the course website, and there's a link there to a little form, and you just fill out like your major, which class you think meets the prereq, and so on, and that's what we'll use as the waitlist for this class. Okay, and yeah, the lectures will be recorded. So the class is pretty full. So if you're not enrolled, we ask that you watch the lectures online. If you are enrolled, please do come to lecture. We have slightly more students enrolled than there are seats, but some fraction of students will typically watch the class online. So if you're an enrolled student and you want to come to lecture, go ahead and come to lecture. The first lecture is always kind of an outlier in that there's usually a lot of people who show up, but as the course goes on, there will be enough seats for all the enrolled students, assuming that not every single one comes in. Yes?
Do you happen to know how to sign up for 3 units instead of 1 unit? Like my default was just 1 unit.
So on Cal Central, you have the option to change the number of units. If you're not sure how to do that, there's a help link, and you can ask for help. Yeah, sorry, I mean, I actually don't have access to the student interface, so I don't even know what it looks like to you.
Sorry, I didn't realize I was like, would you do that?
Yeah. Okay. Well, and with all these enrollment things, if you're really desperate and you don't know how to fix it, contact the GSIs or me, and we'll forward your request to the course coordinator. Okay. So that's the like formal logistics. Now, what you should know for the class, obviously we expect you to have taken a machine learning class. We'll also assume that you are at least somewhat familiar with training neural networks. So all the assignments in the class that we'll give you, they're based on TensorFlow. So if you haven't used TensorFlow before, it's not that hard to learn if you've used other automatic differentiation packages. However, if you are not certain about your TensorFlow prowess, do go online, look up the TensorFlow MNIST tutorial, try going through that. If you find that it's like really easy for you, you're all set. If you find that it's a little bit of a struggle, Josh will actually host a review session in week 3 of the course. So what you do is when homework 1 goes out, you immediately start on homework 1. See if you can do that. If you're having some trouble, go to Josh's section, and Josh will give kind of a crash course on the basics of TensorFlow. And of course, the online TensorFlow MNIST tutorial can also help you. So if you're not sure about your familiarity with this stuff, just most important thing, start early and make sure you get into good shape. All right, so what we'll cover in this class. The full syllabus for the class is on the course website, and that might be modified a little bit as the course goes on and we see how far we get in each lecture, but at a high level, most of the content is there. So we're going to talk about how we can go from kind of the standard supervised learning problem that we're hopefully all familiar with to a decision-making problem, a reinforcement learning or control problem. We're going to cover basic reinforcement learning algorithms like Q-learning and policy gradients. We do expect people to have some basic familiarity with things like MDPs, which you would have probably learned in an undergraduate artificial intelligence course. But for the algorithms, we'll go over them in detail. We're going to talk about model-based reinforcement learning, advanced topics in model learning like prediction, dealing with images and complex observations, distillation, learning reward functions for demonstration, and so on. And we'll talk about more complex deep RL algorithms like trust region policy gradient, sector critic algorithms, advanced techniques for exploration, and hopefully towards the end we'll get a little bit into things like transfer and hierarchy if we have some time. And then we'll, in the last kind of third or quarter of the course, we'll talk about open problems, challenges, advanced research topics. We'll actually have invited lectures where folks will come in and talk about their research, people who are actually doing kind of advanced research in deep reinforcement learning. So the aim of this class is to really get you the background to understand the state of the art in deep reinforcement learning and then introduce you to the open problems and challenges and what is sort of at the bleeding edge of current research in this area. We'll have 4 homework assignments and a course project. The homework assignments are really meant to just give you like a little bit of a primer, a little bit of an introduction, and the main kind of work that you'll be doing in this class is really the final project. So you can think of the homework assignments as just a way to give you a little sampling of some topics in Deep RL, a little bit of an introduction, but the meat of the work that you'll be doing is really the course final project. So we'll have 4 homeworks. The first homework will cover imitation learning. We'll do basic behavior cloning and then a more sophisticated imitation learning algorithm called Dagger. So that'll be in the first few weeks of the class. The second homework will be on policy gradients, where you'll implement the reinforce algorithm, which is likelihood ratio policy gradients. In the third homework assignment, you're going to implement Q-learning with convolutional neural networks. And in the fourth assignment, we'll study some model-based reinforcement learning techniques. And then the final project is expected to be kind of a research-level project of your choice. For all the homeworks, they should be done individually, but for the final project, you can form a group of 1, 2, or 3 people. If you want to make a group of more than 3, please come talk to me. Likely that's possible, but we just want to make sure that the project scope is large enough to really merit a larger group. And for the final project, it's very open-ended. If you're already doing research in deep reinforcement learning or a related area, you're welcome to have the final project overlap with your research. You're welcome to try something new, try something that's a little bit outside of what's covered in the class, so long as the topic pertains to deep reinforcement learning in some way. And if you're not sure, come talk to the GSIs or to me. The grading, very simple. Each of the homeworks is 10%, and the final project is 60%. The final project will include a proposal, a milestone report, and the final report, and those will go into the final project grade. Does anybody have any questions about homeworks, grading, or anything regarding the standards for the class? So we have a mini homework for you today, just a few simple steps. One, if you're an enrolled student, go to the course website and sign up for Piazza. Do this as soon as possible so that you'll receive our notifications. Step 2, start thinking about forming your project groups. Unless you want to work alone, which is totally fine as well, but if you want to work in a group of 2 or 3, a good time to start looking for a project group. You should, if you're an enrolled student, I sent an enrolled student survey to you sometime over the weekend, so please make sure to fill that out. And step 4, check out the TensorFlow MNIST tutorial unless you're already a TensorFlow Pro and don't have to worry about this. If you're a little unsure, check out that tutorial and just make sure that you're really solid on that material. All right, so that's it for course logistics. Today's lecture probably going to be a little shorter than usual, and it's going to be pretty high level. So I'm not going to delve too much into any of the low-level math. That we'll save for the rest of the course. Today, I just want to set up some of the motivation and tell you a little bit about why I think we should care about deep reinforcement learning and all the topics we'll cover this semester. So what is reinforcement learning, first of all? Let's forget for a minute about computers and robots and AI and so on. Let's say that you'd like to train this dog, and you want to train the dog to do something. Maybe you'd like to train it to sit when you tell it to sit, right? One way that you can train the dog is you can reward the behavior that you like and punish the behavior that you don't like, or simply withhold rewards for the behavior you don't like. So long as there's a difference, so long as the animal perceives that things that you like are better for its well-being than things that you don't like, you know, the way that animals typically learn, it'll adopt the kind of behaviors you prefer. So maybe for the dog, you give it a little treat every time it sits after you say sit, and you don't give it the treat if it fails to comply with your commands. So reinforcement learning is basically a mathematical formalization of this principle. In reinforcement learning, you have a learner. That's this little guy over here, sometimes called an agent. If you're reading a robotics paper, they might call it a robot. If you're reading, you know, some other paper, they might call it something else. But somebody who's doing the learning right here. And the agent is going to be interacting with the environment, with the world. What the agent does is the agent makes decisions. So the only thing coming out of the agent and going to the world is its decisions, which we call actions. Sometimes we call them controls also. And the world takes in those decisions and responds by providing the agent with the consequences of its decisions. And there are primarily 2 types of consequences that we're interested in. The first is what the agent can see or perceive as a result of its actions. So those are the observations. So maybe this little robot decides that he wants to, I don't know, walk somewhere, and then he'll observe what he sees when he goes there. And the second consequence that the agent typically gets to perceive is something about how good that decision was, which is the reward. So for the dog, that might be whether or not it got the treat and feels like its hunger has been satisfied. So 2 kinds of consequences and 1 kind of output from the agent. So here are some examples of what these actually might look like for some problems. For the dog, its actions, so the dog is an animal, and the only way that the animal affects the world around it is by using its muscles. That's the only kind of actuator it has, whether it's making vocalizations or moving its limbs. Muscle contractions is how the animal affects the world around it. So those are its actions, those are its decisions. Its observations come from its senses, quite a few senses: sight, smell, proprioception, every kind of sense that the animal has. Those are its observations. And the rewards in this case, maybe it's the food, it's the treats. So those are the things that allow it to understand whether it's doing the right thing or not. If you have Baymax over here, Baymax is a robot, and robots, they affect the world around them by using their motors. So its actions are going to be the motor currents or the torques or whatever representation it has for its actuators. Its observations maybe are the percepts coming from its sensors, camera images, force torque sensors, whatever, joint encoders. And its rewards are obtained from some piece of code that somebody wrote that tells it, for example, some measure of task success. So if Baymax here is trying to learn how to run really fast, maybe its reward is a scalar value that it gets that tells it how fast is it running. If you're solving something that looks like an inventory management problem, an operations research type of problem, maybe you need to decide when to buy additional goods to stock your warehouse. Your actions might consist of the system deciding what to purchase. So maybe, you know, the stocks of widget number 17 is running low, so you decide to buy more of that widget. Your observations are the inventory levels, so you can see how much of each thing you have in your warehouses. and your rewards are the profits. So if you put too much stuff in your warehouse, you have to maybe pay higher fees. If you put too little stuff, then you might not be able to meet demand, and your profits might be lower. So your rewards are the profits that you make. And we can go on and on. We can formulate many, many different problems. In fact, reinforcement learning, as I'll mention later, is actually one of the most general types of formulations of a machine learning problem. Okay, so that's reinforcement learning, but this course is called deep reinforcement learning. So what is deep RL, and why should we care about that in particular? So deep learning refers to end-to-end training of expressive multi-layer models. Very often it actually refers to training of expressive multi-layer neural network models, but not necessarily. So one of the perhaps most familiar examples of deep learning is in computer vision, where models consisting of multiple layers of relatively simple mathematical operators have been extremely successful for doing things like classifying images or detecting objects in images, segmenting images, and so on. A multi-layer model just means that it has multiple layers of mathematical operations, typically nonlinear layers, and those are going to sequentially process some input like an image and produce some kind of output that you care about. Typically, these models are neural networks. The reason that we should care about deep RL is because deep models are what's going to allow reinforcement learning algorithms to solve complex problems end to end. So reinforcement learning provides us with a conceptual framework for thinking about how to solve decision-making problems, and deep learning provides us with the models that can represent solutions to very complex problems. So when we put them together, we can in principle derive algorithms that can solve extremely complex decision-making problems. So what is this end-to-end stuff? And what does it actually mean for sequential decision-making? If you're solving a perception problem like this, let's say you want to look at this picture and you want to recognize that that picture contains a tiger. For most machine learning systems, if they're useful, insofar as they're useful machine learning systems, they're making some kind of decision that affects the world. So whether this is like Facebook trying to figure out if this is a picture of your friend or of a tiger, or whether this is a robot running around in the jungle trying to avoid tigers, somehow it's going to, whatever decision it makes from looking at this picture, it's going to affect something that it does, something that actually affects the world. So typically, you would, if you want to use a computer vision system, what you do is, okay, run the computer vision system, look at what it outputs, and then take its output and use that to decide on an action. That's kind of a conventional pipeline, a sort of systems level approach you might take if you want to incorporate computer vision into your machine learning system. Of course, this action that you take is going to affect what happens next, whether it's Facebook deciding how to classify things in pictures, or this fictional robot running away from tigers. Whatever it decides to do with that picture is going to affect the next thing that happens. So at a systems level, if you have a perception system, probably you also have some decision-making system that's using the results of that perception. That might not be actually a learned system. It might just be a manually designed state machine. But there's some kind of system that uses that to take actions. So if we say that we're going to have that anyway, we're going to use the results of perception or whatever other machine learning we're doing to make decisions, why don't we actually just close that loop? Why don't we say that let's go directly from what we're perceiving to what we're doing? And then we'll have this benefit that we can actually optimize this entire system for the thing that we care about. We can optimize our entire inventory management system to maximize the profit. We can optimize everything for Baymax, from his percepts all the way to his motor torques, for running as fast as possible. And the dog can optimize everything from its senses to the muscle contractions to achieve the largest amount of food. Here are some more concrete examples of how this might work for, I'll give you two examples. One is a robotics example, another is a video game example. So in robotics, if we want to, let's say, design a robotic system, a pipeline for robotic control out of a set of components that we can, maybe open source components that we can find on the internet, we can think about it like this. The robot is going to have some observations. Maybe it's going to perceive pixels in an image. It's going to need to look at that image, understand what's in it, so it's going to do what's called state estimation, basically computer vision. Maybe it needs to operate a tool, so it needs to find where that tool is. It's going to have some kind of modeling and prediction component. So it's going to detect these things, and then it needs to figure out, like, what are these things in the world? What are they going to be doing? So maybe there's like a physics simulator, or at least a kinematic simulation that is going to predict the effect of the robot's actions on the world. Maybe then there's going to be a motion planner. This is a very popular way in robotics to make decisions. And that motion planner is going to provide inputs into a low-level controller that will actually choose the torques or motor commands to get the robot to perform these tasks. So this is kind of a more traditional pipeline approach for decision-making control in robotics. We can look at an analogous pipeline if we want to code up a bot to play a video game. Sorry if this is a little bit of an antiquated example. This is a video game from the late 90s, but same applies today. If you want to code up a bot for playing a video game, well, maybe its inputs are not going to be camera images. Its inputs are some sort of game API. You're going to use that API to extract some relevant components of the game. Maybe it has to look at where the opponents are. It has to look at some other parameters. Then maybe you build a state machine that says, like, okay, if your opponent has a higher score than you should go out and try to beat them. And if your opponent has a lower score than you, then you should be more defensive or something. Some kind of state machine that describes at a high level what the bot should be doing. Then maybe there's a planner that will actually decide how to execute each of the boxes in the state machine. That planner goes to some low-level controller, which actually controls the bot in the game. Maybe tells it where to shoot if it's like a shooting game or something. All right, so same principle, that each stage is designed manually. Each stage pulls out some sort of representation, some sort of abstraction about the world, and that abstraction is passed on to the next stage, which has to solve, hopefully, a simpler problem. The trouble with both this framework and the robot control framework is that because every stage of the representation introduces some abstraction, it loses some kind of information. So you have to really make sure that the abstraction that you pull out about the world is the right one, because you're losing everything that came before it. So if, when the robot localizes things in images, it pulls out exactly the right information about that image, it's okay for it to throw out the image pixels. But maybe it didn't localize things correctly, or maybe there's some aspect of the appearance of an object that's relevant to the task that it just threw out. And the same for the bot. Like once it goes past the state machine, it decides on a particular strategy. Now if there's some other relevant feature over here that it needed to inform that strategy, that has now been lost. So pipeline approaches are great because they allow us to build abstractions that simplify downstream processing, but if we're building those abstractions manually and we don't build exactly the right ones, then we get suboptimal performance. Now, this story is not actually all that new. In fact, in computer vision, if you go back maybe 10 years or so, the way that we designed computer vision systems was largely analogous. We would actually go in and we would pull out some, let's say, low-level representations like a histogram of oriented gradients, would pull out some mid-level representation and discard the stuff that came before it. And then on top of those, we'd build, let's say, a classifier to detect the thing we wanted to get. With deep learning, there are still multiple layers of representation in here. It's just that now these multiple layers of representation are actually adapted to the task, which means that we no longer have the need to manually craft the abstractions and the interfaces between these layers. They're optimized to achieve the best performance on the task we care about, which might be classifying the tiger, with end-to-end training. So you get a lot less manual effort to design the abstraction, and the abstraction that you do get, the representation that you get, is optimally adapted to the task at hand. So end-to-end training with deep reinforcement learning in principle holds the promise of doing the same thing for these control pipelines, whether it's robotic control or inventory management or implementing a bot to play a video game. If you can go in and say, okay, we'll do end-to-end training on this whole thing and replace it with learned components, then we don't have to manually design each of these boxes or craft exactly the right interface between them. So that's kind of the motivation. That's why we'd like to be able to develop deep reinforcement learning algorithms that can actually take us all the way from raw sensory percepts to the actions that we'd like our system to execute. So to make this a little bit concrete, you can imagine, for instance, a deep reinforcement learning algorithm might allow you to say, okay, here's my robot. Its sensors go into the bottom of a deep neural network. The deep neural network at the top outputs motor commands that go to its joints. So maybe these are images, these are its motor torques. And this neural network then encompasses the entirety of that robot's decision-making apparatus, a sort of minuscule version of a brain, if you will, with a really tiny, to horribly torture the analogy, a really tiny visual cortex that processes images, maybe using convolutional layers, and a really tiny kind of motor cortex that processes the features and outputs motor commands. Don't take this analogy too seriously. And there are two big challenges that come up if you want to do something like this as opposed to the more traditional kind of fully supervised deep learning. The first challenge is that typically when we're doing deep reinforcement learning, we don't have direct supervision. The reason that we want to do reinforcement learning is that there isn't anybody there to tell us that when you see this image, execute this motor command. The supervision is more indirect. Like for the dog, the supervision is did it get the treat or not what the correct muscle contractions are to perform the task. And the actions have consequences, which means that it's not enough to simply make one decision correctly. You have to make an entire sequence of decisions until you receive the outcome that you want. So the way that, at a very high level, that most deep reinforcement learning algorithms will work is through something that resembles trial and error, where you will actually have the system attempting to do the task, observing the outcomes, and then adjusting its strategy. So for the robot, it might look like this. So here the robot is attempting this task. It's trying to put the little toy into the shape sorting cube, and it just keeps trying until it gets it right. All right. So just to review, the reinforcement learning problem consists of a learner or agent that is interacting with the environment. The learner or agent produces decisions, which are actions. The environment, in response, produces two types of consequences, observations and rewards. And this might apply, for example, to robots whose actions are currents or torques, and whose observations are maybe images from their camera or proprioception. It can apply to inventory management, and it can apply actually to lots of other problems. So you can imagine even framing, for example, machine translation as a reinforcement learning problem, where the actions are, let's say, words in a target language, like words in French. The observations are words in a source language, for example, words in English. And the rewards are some measure of the quality of the translation. So blue score is a very popular choice here, for example. In fact, almost any problem that can be framed, well, not almost, actually any problem that can be framed as a supervised learning problem can be reformulated as a reinforcement learning problem, with the caveat this might not always be a good idea. And the way you reformulate any supervised learning problem as a reinforcement learning problem is to say the inputs are the observations, the outputs are the actions, and the reward is whatever loss function you want to use. Now I said this might not always be a good idea because typically reinforcement learning makes fewer assumptions than supervised learning and therefore is a little bit harder to solve. So even though you can reformulate any supervised learning problem as a reinforcement learning problem, that doesn't mean it's always a good idea. But sometimes it could be. For example, blue score is not a differentiable measure of the quality of a translation, so you could incorporate it into a reinforcement learning framework, but not most supervised learning frameworks. So the reinforcement learning problem is essentially is the AI problem. It's one of the most general ways that you can formulate a learning task, and it allows you to subsume pretty much any other kind of learning problem, although again, that's not necessarily the best thing to do if you want to actually solve something. And since reinforcement learning is the AI problem, if you can allow reinforcement learning algorithms to solve very complex problems, then you will have come a bit closer to actually building useful AI. And deep models are what allow reinforcement learning algorithms to solve complex problems. So that's why we're interested in deep reinforcement learning. Okay, so just to wrap this up, when do we not need to worry about sequential decision making or reinforcement learning? When your system is making a single isolated decision, basically when the consequences of its actions are not going to affect what it sees next, like classification or regression, and when the decision doesn't affect future decisions. So if you're classifying images, if you're recognizing text and so on, typically these are not formulated as reinforcement learning problems, although they could be. And when should you worry about sequential decision making? When you have limited supervision, for example, when you know what you want but not how to get it. So the dog, for example, knows that it wants the food, but it doesn't know how to move its muscles to get the food. And when your actions have consequences, when a single decision doesn't immediately produce the outcome you care about, but actually a sequence of decisions is necessary until you see whether you got it right or wrong. So this is the case, for example, in a lot of problems in robotics, for self-driving cars, in a lot of language and dialogue, kind of structured interaction settings, business operations, finance, and so on. So there are numerous applications that involve decision-making with delayed consequences and limited supervision. Okay, so that's why we should care about deep reinforcement learning. But why should we care about it now? There are basically three reasons. I think there's three at least. So one is that we've seen a lot of really impressive advances in deep learning in the last few years, which have allowed us to actually build the kind of expressive high-capacity models that we need to represent solutions to very complex decision-making tasks. We've seen advances in reinforcement learning and building algorithms that are scalable enough to actually train these models for decision-making problems. And we've seen advances in computational capability that make it actually practical to train models that are large enough in timeframes that are actually feasible, that are useful for solving real-world problems. So these are three very practical, pragmatic reasons why we should care about this now. That said, the idea of incorporating high-capacity nonlinear models into decision-making is not by any means a new one. In fact, you can go back to the late 80s and find textbooks on using neural networks for control. These are some excerpts from a PhD thesis written in 1993 that points out a few things that are actually kind of cutting-edge research topics today. for instance, reinforcement learning can be naturally integrated with artificial neural networks to obtain high-quality generalization. That's basically stating that deep reinforcement learning is a good idea. Experience replay is a simple technique that implements this idea and shows can be effective in reducing the number of action executions required. We'll learn about experience replay as a way of improving sample complexity when we talk about Q-learning later on in the course. This was a technique that was reintroduced for convolutional neural nets around 2013. Reinforcement learning agents can take advantage of instructive training instances provided by human teachers. This is a description in not so many words of curriculum learning, which we might get a chance to cover as a very advanced topic towards the end of the course. Reinforcement learning agents can significantly reduce learning time by hierarchical learning. First solve elementary learning problems and then combine solutions to the elementary problem to solve a complex problem. This is actually still an open problem. We actually still don't know how to do this, turns out. But the idea has been around for a very long time. Reinforcement learning agents can deal with a wide range of non-Markovian environments by having a memory of their past. So I'll mention using recurrent networks with memory as a way to deal with non-Markovian environments actually multiple times during today's class. So the point is that the core underlying ideas have been floating around in the community for decades at this point. It's just that the three ingredients that I had on the previous slide just haven't all been in place to allow us to fully implement them. That said, deep reinforcement learning methods have had very successful kind of milestone results decades ago. So one of the better known examples here is the what's called TD Gammon, which was a backgammon playing bot developed by Jared Tesoro in 1995. And this was actually one of the first big successes of what we would today call deep reinforcement learning, neural networks, multi-layer neural networks combined with reinforcement learning algorithms that could actually beat very proficient human players, in this case at backgammon. The principles behind this were basically large fully connected neural networks coupled with temporal difference learning. And we'll study temporal difference learning in this course. That said, very recently we've seen some very impressive results that combine deep learning and reinforcement learning across a range of different domains. So with for example, learning to play Atari games using Q-learning, policy gradients, and a variety of other techniques, learning to control robots with policy search algorithms and Q-learning, and of course the result that many of you are probably familiar with, learning to play Go, actually through a combination of supervised learning, imitation learning, and policy gradients. So the combination of those three factors I mentioned before, the advances in deep learning, scalable reinforcement learning algorithms, and computational power, have enabled a lot of the potential of these methods to begin to be realized in recent years. Okay, so what other problems, other than building better reinforcement learning algorithms and better deep models, do we need to solve to enable real-world sequential decision-making? So in this class, we're going to study the core reinforcement learning algorithms, as well as the kind of techniques that are necessary to make them scale to deep models. But we'll also study a number of other topics that are very important to actually bring reinforcement learning into real-world settings where the conventional assumptions might be a little tricky. There are a few that we're going to look at. One is going to address this kind of issue that only really, I think, becomes apparent once you think about reinforcement learning in the real world. So basic reinforcement learning deals with maximizing rewards. But this isn't actually the only problem that matters for sequential decision-making. So, for example, sometimes even specifying what the reward function is for very complex tasks is difficult. It requires a bunch of additional engineering or a bunch of additional learning, in fact. So we're going to talk about how we can actually learn reward functions as well from examples, from observing people doing things. We're going to talk about transferring skills between domains. So sometimes you don't have enough time or enough bandwidth to learn a skill entirely in a target domain, but you'd like to use your past experience to accelerate that. So we're going to talk about transfer learning. We're going to talk about learning to predict and using prediction to act. So sometimes you can obtain lots of experience where you can observe how the world works, understand things like physics, but not necessarily observe the rewards or the goals of the tasks that you want to accomplish, and you'd like to use that predictive power to then accomplish a new task. So we're going to talk about that as well. Let me very briefly kind of allude to what some of these topics will look like. So let's talk about rewards first. If you're learning to play a video game, there's a very natural notion of reward in a video game. That's the score of the game right up here. So it makes a lot of sense to say that, well, in a video game, your reward function comes from the score in the video game. But let's say that you want to build a robot to pour a glass of water. So that's something that this kid here can do pretty well. He looks at this little jug of water, he says, oh, I just need to pick this up and I just need to tip it over into the glass and I'll get a glass of water. Building a reward function for this task to get a robot to do this is exceptionally difficult. This is basically an open problem in computer vision. Detecting how much water there is in the cup, you probably need to generate a training set, you need to label that training set, who knows how you're going to do that. It's like a big research project just to evaluate the reward function for something like this. And in fact, if we take a kind of absolutist view of reward, we say like the reward is the thing you finally want at the end of your long existence. This is actually not a very natural notion of reward. This is a quote that I really like from a paper actually written by some folks here at Berkeley. It says, as human agents, we are accustomed to operating with rewards that are so sparse that we only experience them once or twice in a lifetime, if at all. So imagine what is the sort of the goal of a human agent? Well, as animals, one might say our evolutionary goal is to make more humans, so that's something that most people do a limited number of times in their lifetime. Maybe our goal is to find food so that we're not hungry. These are not things that happen like minute to minute, so these are like extremely delayed and fairly rare events. Now this is a screenshot from Reddit, so of course somebody read this paper and what they said is, I pity the author. Research is tough, what can I say? But actually, like if we look at some of the kind of the biology underlying this, there is a part of the brain that is widely believed to be responsible for rewards. For like when people actually do something that looks like reinforcement learning, we kind of know where they come from. They come from here, right? This is not some sort of magical box that receives external signals that tell it like you've done a good job. This is a part of the brain, a fairly complex one, that evolved to provide the kind of rewards that induce, presumably evolutionarily favorable behavior in humans. So this is not something that we can just say, oh, there's just a score, a magic score that comes from some magic place that we just assume always exists. This part we have to deal with. We have to figure out where it comes from. And if you look at the behavior of animals, for example, if this cheetah needs to hunt down the gazelle in order to survive, the cheetah can't just like randomly flail its limbs around until it happens to catch a gazelle. It has to have a little bit more of a sense of direction in order to get far enough to receive even a single thing that we might count as like a true reward. So rewards are complicated, and assuming that they're always going to be present and perfect might be a fairly strong assumption. So are there other forms of supervision we can look at? And we'll discuss this later in the course. We can think about learning from demonstrations. So we can think about watching how other successful agents perform tasks and what we can learn from that to perform those tasks successfully. So we can think about directly copying observed behavior. We'll actually talk about this next week. This is sometimes referred to as behavior cloning. We can also talk about a more sophisticated form of learning from demonstrations where instead of copying the behavior of an agent, you actually copy their intent. So you look at what they did, try to figure out why they did it, and then figure out your own way to satisfy that goal. You can learn from observing the world around you. So you could, for example, learn to predict, understand the physics of the environment. And if that cheetah, for example, understands the physics of how it might interact with a gazelle, it might have an easier time figuring out how to catch it without necessarily relying entirely on trial and error. We can think about using unsupervised learning. So if you observe the world around you, there are certain structural regularities that you can pick up on in the visual world or in your other senses that can accelerate learning. And you can also learn from other tasks. And this is something that people actually do very well. So you can imagine, for example, doing transfer learning. If you've learned another structurally similar task in the past, you can use what you learned from that task to dramatically accelerate the learning of a new task. We can also think about meta-learning, which is closely related to transfer learning, but different in a very subtle way, which is to use your past experience of learning other tasks to figure out how to learn more quickly. So this is, you can think of, for example, of experimentation. You can say, okay, well, I don't know how to solve this task, but in the past, the way that I've solved tasks is by trying A, B, C, and D. So let me try A, B, C, and D and see how that works out in this new setting. Now, imitation learning is actually a very reasonable way to solve many sequential decision-making problems. This is a video, this is from a paper actually from NVIDIA research that shows an autonomous driving system built entirely using imitation learning. And I'll discuss this a little bit more next week. So this is a system that was trained from observations of human drivers without any notion of a reward function and without any kind of reinforcement, what we would call conventional reinforcement learning algorithms, just by copying human drivers. Now, of course, the video is a little bit idealized, but the point is that, yeah, you can do some pretty complex things just from observing expert humans. Inferring intention is something that actually humans do very, very well. This is a video from a study of children where this well, I guess you'll see what happens. So this guy here, you can kind of tell what he's trying to do. He has a bit of an issue there. And this kid here, he's observing this behavior. You know, children often mimic the behaviors of adults. But the kid here is not going to directly mimic what the adult is doing. What he's going to do is he's going to figure out what is the intention of the adult and go in and help him out a little bit there. So our robots can think about doing things like this. This is an example of what's called inverse reinforcement learning. So reinforcement learning means reward goes in and behavior comes out. And here behavior goes in this case, this is a demonstration, what's called a kinesthetic demonstration for the robot to show it how to do a pouring task. And the robot can analyze this behavior, figure out what is the goal of that behavior, understand that it's really the yellow cup that matters here, so it needs to go near the yellow cup, and then it can figure out that when you put the yellow cup in a new place, it can then use forward reinforcement learning to re-optimize that goal and perform the pouring task. Okay, prediction. So reinforcement learning deals with learning skills, learning behaviors, learning how to map from your observations or states to actions. You can also learn to do prediction, which means to map from your states and actions or observations and actions to the next state or observation. Prediction is known to be a central component of what brains actually do. A lot of what brains do is prediction. The idea that we predict the consequences of our motor commands emerges as an important theoretical concept in all aspects of sensory motor control, and these are academic works on sensory motor control that study how humans and animals do prediction. If you can do prediction, if you can predict the consequences of your actions without having to actually execute them, if you can just imagine what will happen if you do a certain thing, then of course you can achieve goals by taking the actions for which your imagination tells you that you'll succeed, instead of relying entirely on trial and error. So if we're lucky enough to have a perfect model, if, for example, we have a prediction model that truly accurately and perfectly predicts everything that will happen in the future, we can actually synthesize extremely complex behavior. So this kind of experiments are typically done, of course, in simulation. If we have a simulation and we want to act in that simulation, we, by definition, have a perfect model. So if you have a simulation, it's actually quite possible to build extremely complex skills. So what this video is showing is some actually user-directed locomotion skills where this little guy learned to walk to the position that the user is indicating by using a combination of deep learning and a trajectory optimization procedure that uses a known perfect model. And we'll talk about how you can act under perfect models when we talk about model-based RL. So this is not learning the model, this is just saying, okay, if you have a model, can you do really complicated stuff? And the answer is that yes, you can, and it turns out that you can actually do stuff that is more complicated than what you could do if you didn't know the model. If you don't know the model, however, and you want to use prediction, you have to learn what the model is. You have to learn to predict. This is a video from an experiment on learning to predict with raw images. And what was done in this experiment is actually you had a number of these different robots, and the robots interacted with the world around them, just kind of randomly playing around with it and seeing the outcomes of their actions. So the actions here are just random. They're just pushing stuff around on a table, and they're recording the images and the actions that they took. And if you can record the images and the actions that you took, then you can use that to learn to predict. So what you're actually going to be predicting here is images. The top row here shows a video from the robot's point of view, so the camera is right up there, that little black box, so it's kind of over the shoulder. These are the true videos that the robot saw, and these are predictions. The way that these predictions are made is by looking at the first frame in the video and the sequence of actions that the robot will take, and trying to predict what the raw frames will be. This is done using recurrent convolutional neural networks, and we'll talk about these kinds of techniques later in the course. Once you can build predictive models like this, you can do control. You can basically say that, well, now the user is going to give me some goal. I'm going to imagine the consequences of different actions, and I'm going to take the actions that I imagine will fulfill the user's goal. So here's what this looks like. Here, the user clicks on some point, clicks on where they want the point to go. So red is the source, green is the destination. The robot thinks for a while, imagines the outcomes of different actions, and then executes the actions that will actually bring about the outcome that the user requested. So this is what's called model-based reinforcement learning. All right, so that's kind of the more technical part of today's lecture. For the remaining maybe 15, 20 minutes, I'll talk about something a little bit more speculative. I think there's a lot of very practical reasons why we should care about deep reinforcement learning. But I think that another reason that we should care about it is it'll help us to understand how we can build intelligent machines and how we can actually understand our own intelligence. There's a question, yes?
Sorry, I don't mean to interrupt, and also if you're going to kind of cover this later, of course, answer. But like in the vein of going through examples,
Mhm.
I'm curious if there's any RL being used for like socioeconomic data,
Mhm.
some sort of things that's not centered around just like robotics or agents.
So we will talk a little bit about various applications as the course goes on. Off the top of my head, I'm not aware of something, but if I think of it, I'll let you know. Okay, so in the remaining part of the lecture, I'm going to talk about some thoughts about how the ideas that we're going to study in this class can help us move towards building intelligent machines. So let's back up a little bit and let's think about this question. How do we build intelligent machines? So imagine for a minute that you weren't thinking about reinforcement learning or machine learning. I just told you, okay, time to build an intelligent machine. A machine that thinks like a person. Where do you start? Well, as an engineer, you know, we think a lot about building systems out of modular components and imagining the right kind of abstraction and so on. So we might say, okay, well, let's try to engineer an intelligent machine. We can look at a brain. We can say, okay, well, the brain has a bunch of parts. The parts do different things. This is maybe a rather antiquated picture of the parts of the brain. There's a bunch of modules. Those modules are doing different jobs. So let's try to build each of those components. If we can succeed at building each of those components, we can plug them together, and out will come something that looks like intelligence. Now, this is, as I said, an antiquated picture. We have a more modern picture of the different parts of the brain. They all do different jobs, so let's you know, split up into groups and go and build each of these parts. That's a very reasonable way to think about building an intelligent machine. In fact, based on everything that we know about how to engineer complex systems, this is a very natural place to start. The trouble is that once we start working like this, then we'll quickly end up with a situation where each of these modules kind of does something similar to what it's supposed to do, but it ends up being very brittle. It's not able to flexibly adapt to changing situations, which is really one of the hallmarks of intelligence. So then we step back a little bit and we say, okay, maybe this wasn't such a good idea. What if we think about learning as a basis for intelligence? Well, that sounds kind of, you know, a little extreme, but here's a little bit of a rationale for it. There's some things that we can all do really well. Like most people who have who are not disabled, if they can walk, you know, we can all walk like pretty well. Unless we have a physiological reason that precludes us from doing that. So as far as how our brains work, you know, typically that seems like maybe it might be innate. It might not be something that we have to learn. But there are some things that we can only learn. Like there's no way that people can possibly be evolved to drive cars because cars weren't around when humans first evolved. So there are some things that we can learn. And these things that we can learn, they're hugely varied and they're very difficult. Like we can learn some pretty complex stuff that we can't possibly have been evolved to do. So from this one, I conclude that our learning mechanisms are likely to be very powerful and, in fact, might even be powerful enough to do everything that we associate with intelligence. So it might still be very convenient from an evolutionary perspective to hard code a few really important bits, like there are some things that you really need to do really fast, you don't have time to learn it. But if the underlying learning mechanism is powerful enough to do everything that we associate with intelligence, perhaps what we really need to do is we need to figure out that learning mechanism, and then the few bits that we need to hard code, I mean, fine, it's like we do that on a case-by-case basis. So that's maybe a hypothesis, a guess, if you will. Okay, now we have this picture of the brain does different things, and now we say, okay, learning is the basis of intelligence. So let's say that we build a little learning algorithm for each of these components. We have a little learning algorithm for learning to see, a little learning algorithm for learning to move, and so on, and then we wire together those learning algorithms. But should it really be a different algorithm for each module, or can we get away with a single algorithm? Well, the trouble with having a different algorithm for each module is that now you've taken this problem of building this really complex system and you've changed it into a different problem of building a really complex system, which might actually be harder because building learning algorithms is difficult. Like designing a new learning algorithm from scratch takes a lot of time. But maybe we don't need to do that. Maybe we just need a single, very good algorithm. When it comes to perception, at least, there's good evidence that something like this may be true. And the way that you can get that evidence is by studying plasticity, studying how people can learn to perceive things in ways that are not the way that they usually perceive them. So you could, for example, build an electrode array that you can put on your tongue, attach that electrode array to a camera, and you can learn to perceive the world with your eyes closed using your tongue. People who are blind can learn to perceive the world around them using sounds. And perhaps one of the better known experiments in this area, this is sometimes referred to as the ferret rewiring experiment. This is an experiment where ferrets, very young ferrets, had a little surgery where their optic nerve was actually disconnected from their visual cortex and then reconnected to their auditory cortex. And then after the critical period, after they mature, the scientists tested whether they could actually perceive with their eyes, whether they had some degree of visual acuity. And it turns out that they did after an adaptation period. So that suggests that whatever is going on here in the auditory cortex is general enough that if you hook up a pair of eyes to it, the ferret will actually learn to use them. It'll actually learn to process the signals coming from the optic nerve, which seems very peculiar because that's not an event that typically happens to the ferret in nature. So that suggests that for whatever reason, its sensory cortices may be implementing an algorithm that is general enough to process whatever kind of sensory input might be coming in. Now that's just for sensing, of course. Okay, so if we're going to hypothesize that we can build a single algorithm that can fill in basically all of these boxes over here, one question we might ask is, well, what should this algorithm be able to do? What are the requirements? You know, when you're engineering a system, you write down the specifications. What are the requirements? Well, it needs to be able to interpret rich sensory inputs, because one of the hallmarks of intelligent systems is they can process rich sensory inputs from sight to sound to images to reading text on a page. And they need to be able to choose complex actions. So they need to be able to execute dynamic and flexible movements to affect the world around them. And movements in the general sense, maybe abstract actions for an agent, you know, buying or selling stocks, all the way to actual physical movements for a robot. So why might deep reinforcement learning satisfy these requirements? So the deep part is what can allow us to process complex sensory input and also compute really complex functions. And I'll talk about some research that tries to study whether or not this is true. And reinforcement learning is what can allow us to get started on choosing complex actions. So let's talk about deep learning and processing complex sensory inputs. This is a paper that, those of you that are interested in the connection between deep learning and the behavior of sensory cortices in the brain, strongly recommend checking out this paper by Andrew Sachs. This paper studies the statistics of features learned by deep learning algorithms, and deep learning algorithms circa around 2011, and the statistics of features that are actually observed in fMRI and electrode data from brains. And they study different kinds of senses. They study sound, vision, sound, and touch. So for visual features, what they do is they train deep networks on large image data sets and then study the statistics of features when exposed to various stereotyped stimuli like edges and these kinds of funny patterns. And these are experiments that had previously been done on humans and animals to try to figure out the statistics of features in the visual cortex, and they basically compare those statistics to the statistics of features learned by a neural network. I should clarify here, this does not actually mean that a neural network works the way a brain does. It just means that the features that it pulls out have similar statistics. That could mean, for example, that the statistics are actually just there in the environment, and any sufficiently powerful function approximator when exposed to environments with those statistics will acquire features that have those statistics. But for our purposes, that's good enough, because what we want is a system with comparable capability, not a system with comparable implementation. Auditory cortex, same story, that the kind of features observed when exposed to stereotyped sound patterns look similar in the sense that they have similar statistics between animals and deep networks. This is kind of a funny experiment. This is studying features observed in somatosensory cortices in monkeys. The way the monkey experiment is done is that the monkey's hand is placed on a rotating drum with indentations on it, and then you can record the statistics of basically features of tactile sensing in the monkey's brain, because you know the pattern of touch on its hand from what the drum looks like. And then for the deep neural network data, they had this funny setup where they take a glove and they have a person touch an object that's been dusted with white dust, so then the dust gets deposited on the glove, and they can look at the pattern of with which the person touched the object, and they can use this to train their deep neural network to look at the kind of features that picks out. So, long story short, the kind of statistics that you observe in sufficiently powerful deep neural network representations seem to look an awful lot like the statistics of features that you observe in brains, at least at the lowest levels. What about reinforcement learning? Well, reinforcement learning actually started out as a study of how animals learn. It only later on got imported into artificial intelligence as a convenient way to think about decision-making in computational frameworks. So there is, for example, evidence that percepts that anticipate reward become associated with similar firing patterns as the reward itself. And this is what in reinforcement learning we would call the Bellman backup, and we'll learn about that when we talk about model-free algorithms. There's evidence that the basal ganglia appears to be related to the reward system in the brain, and that can be correlated to this backup with the percepts. And model-free RL-like adaptation is often actually a good fit for experimental data of animal adaptation, which means that you can use a model-free algorithm to predict how the adaptation will occur, and you observe adaptation patterns that are similar, but not always. So it seems to be part of the story, but not the entirety of the story. So this is maybe some evidence that regardless of how the mechanism is implemented, the end result of the mechanism looks kind of similar to reinforcement learning algorithms. So this suggests, reinforcement learning maybe might be a good way to think about action, and deep learning might be a good way to think about processing complex sensory inputs. All right, so that's maybe the more optimistic side of things. And let's just conclude that optimistic note by thinking about what can deep learning and reinforcement learning do very well now. So if we take the best of these pieces that we have now, put them together, what kind of stuff can we do that might suggest that this is on the way to developing intelligent machines with capabilities that are similar to what we see in human and animal intelligence? Well, reinforcement learning algorithms can acquire a high degree of proficiency in domains governed by simple known rules, things like board games, video games. If we know the rules, we can just do a really great job of building intelligent agents that can behave successfully in those domains. They can learn simple skills with raw sensory input given enough experience, so things like having a robot grasp objects or having a robot do like simple, relatively short manipulation skills. And they can learn from imitating enough human-provided expert behavior. So if you have humans, they can give enough examples. These kinds of techniques can learn fairly complex skills. But what has proven to be challenging? So this is the downside of this. What is it that where it falls short? Where it seems like we've got the right parts, but they're not quite cutting it. Well, one of the things that humans and animals can do is that they can learn extremely quickly. This is a picture. This is a diagram of a very common motor adaptation experiment where a person has to hold. It's sort of like a joystick attached to a lever, and they're told to move to a particular location. The lever exerts a force to perturb their motion. Humans can adapt to this force in just a few trials. They can figure out which way they're going to get pushed, counteract it, and succeed at the task. Much, much more quickly than one would think you could achieve with a reinforcement learning algorithm. So somehow humans learn extremely quickly, perhaps by repurposing past experience, or perhaps by figuring out exactly the right dimensions along which to adapt. Deep RL methods are usually pretty slow. So humans can reuse their past knowledge. Humans are very proficient at this. And transfer learning in deep RL remains an open problem. And it's often not clear what the reward function should be, so I alluded to this previously. It's also not clear what the role of prediction should be. So we have ways to do prediction, we have ways to do reinforcement learning, but it's not really quite clear to us exactly how those fit together. All right, so to summarize this part of the lecture, if you want to think about building intelligent machines, one of the things you could do is you could say, well, an intelligent machine needs to have all these different parts in its machine brain, so we can go and build those little parts and try to wire them together, but that ends up being very difficult, and the kind of machine brain that we get often ends up being rather brittle. So if we can simplify things, and if we can be successful in designing a single algorithm that can actually do the job of learning everything that this brain needs to do, if we can simplify things to a general learning algorithm interacting with its environment, maybe we'd have an easier time of doing this. And I mentioned before that a lot of the ideas in deep reinforcement learning, they've been around for a number of decades, and this idea is no exception. This is a quote that I really like. Instead of trying to produce a program to simulate the adult mind, why not rather try to produce one which simulates the child's? If this were then subjected to an appropriate course of education, one would obtain the adult brain. This is from Alan Turing from the 1950s. All right, I'll see you all next week.